Swayam Prabha. Digital India. Educated India.
Okay, moment you let us say type in your Google strain displacement gradient, this figure is the most popular figure you will come across. Okay. Same figure has been taken from Raymond Parnas, and let us understand this gradually. The x axis, y axis are shown, okay, and then a plate PQRS is shown in the initial state undeformed configuration. Now, two ways of visualizing this. One is, as I told you, a plate, the easy to understand. Other way you should understand is it is a square region inside a solid object, because as you see, as you will see as we go along, we will make the plate to a point as usual. So, then of course, you can't say it is a plate. So, two ways of imagining, it is a plate to usual observation or a two dimensional region in a solid object, okay, fine, and that is denoted by PQRS. The length of the sides are delta x, delta y. Now, this plate is subjected to a force and it has taken a final state denoted by P star, R star, Q star. S star is not denoted because it is not important for us, but anyway that boundary is this, you can say as S star, S star. So, PQRS plate has become P star, R star, Q star, S star. If you look at compare P star, the final state and initial state, easily you can understand that there is change in length. PR is not same as P star, R star, there is normal strain. Similarly, P star, Q star and versus PQ. Look at the angle, there is change in angle. Look at the rotation, there is rotation. What about translation? Yes, there is translation. So, we have considered the most generic configuration. The initial plate has undergone translation, it has undergone rotation also, there is change in length also, change in angle also, that is what we want to represent. Okay. Okay. Now, coming back to the description, let us focus on P and P star. P has moved to P star, or more formally P has got displaced to P star. How do you represent it? As P and P star are relating x displacement. So, if you look at this one, it says the distance between P and P star is x displacement, and then that depends on the, remember ux uy depends on x and y. So, it is evaluated at x comma y. Okay. This nomenclature we have seen earlier for our derivations. The vertical bar tells you that we are evaluating at a particular location. We not come across two subscripts, but now ux is evaluated at x comma y. Okay. Repeat again, P has got displaced to P star, that displacement is ux, fine, but that depends on where P is present. The coordinates of P are x comma y, x comma y. So, ux is evaluated at x comma y. Now, what about Q? Because the length of PQ is delta x, the x coordinate of Q is x plus delta x. So, this coordinate if you mention, it is x plus delta x, of course same y coordinate is y. So, Q has got displaced to Q star and x displacement is ux, evaluated x plus delta x comma y, okay. Same like as we had done for control volume, one phase is x, other phase x plus delta x. Similarly, here looking at 2 points. So, one tells you displacement at x comma y, other tells you displacement at x plus delta x comma y. Now, P and P star and Q star have undergone vertical displacement also. Now, we are looking focus only on the horizontal displacement. Now, let us focus on the vertical displacement. P from this location has moved to P star here, and that is what is denoted here as vertical displacement uy, once again evaluated at x comma y. Okay. So, uy vertical displacement, that is a vertical distance between P and P star and evaluated at x comma y. Now, Q has also shifted to Q star, moved to Q star, vertically displaced. So, this position is Q star, this is Q, What is the vertical displacement? uy, but where is it evaluated now? X plus delta x comma y is evaluated at q. So, uy evaluated at x plus delta x comma y. Okay. So, we have completely described all the nomenclature shown. One thing is left, I will describe that as well. What else is shown? The angle p star q star makes horizontal as alpha, which means that the element PQ has undergone a small rotation of alpha. Similarly, PR has undergone a small rotation of beta to P star R star. Okay. So, all the nomenclature has been discussed. Just to summarize, plate PQRS in the initial state goes to P star R star Q star S star in the final state, and we have discussed all the displacement x direction. We have discussed x displacement of P, x displacement of q, and then similarly y displacement of p and q, and we also discussed what does alpha and beta represent. Okay. With this nomenclature, let us proceed, and that is what is shown here. Displacement as a function of x and y. X displacement of point P at x y is equal to u x evaluated at x comma y. X displacement of point Q which is at x plus delta x comma y is u x evaluated at x plus delta x comma y. Now, talking about y displacement of point P is u y evaluated at x comma y. Y displacement of point Q which is little away along the x axis is u y evaluated at x plus delta x comma y. Okay. Okay. Now, we are proceeding towards deriving a relationship between normal strain and displacement gradient. Okay. Okay. Now, let us start with the definition of normal strain. What is the definition of normal strain? Change in length by original length. We define introducing epsilon n n. The way to begin with, we said epsilon n n. Okay. Now, our direction is along x axis, because we are going to consider the line element p q. So, that is why this is epsilon x x, normal strain for line element oriented along x axis. Now, what is the final length? Final length is the length of p star and then q star. Okay. So, length of p star q star. What is the initial length? This length of p q, length of p q, divide by initial length p q. Okay. So, something known to us. But now, this change in length by original length in the limit of delta x tending to 0. That is why I told you two ways of imagining. One is imagining as a plate, easy to visualize. Other one is a 2D region inside a solid object, and as usual we want a local point form of relationship between normal strain and displacement gradient. Any relationship should be valid at every point. That is why the relationship which we are going to derive is valid at every point inside a solid object. Okay. Okay. Now, so we have to evaluate this change in length by original length in the limit of delta x tending to 0. Now, I will make an assumption. Infinitesimal rotation. What do I say? P q slightly rotates, very small, extremely small, to p star q star. Okay. What happens in that case? Instead of taking this length p star q star, I will take the projected length of p star q star. Instead of taking this length, I will take only this length. So, I will repeat again. Actually, I am supposed to take the actual length of p star and then q star. Because the rotation is very small, I am not going to take this actual length, but I will project this q star and I will consider only this length as same as this length, which is very much valid when the alpha is very small. That is assumption. Infinitesimal rotation, that is alpha less than 1. Now, what is the length of projected p star q star? Okay. Please keep that in mind. We are going to write this, that is my final length to some approximation. Okay. So, let us write down epsilon x x, limit x, delta x tending to 0. We have to write expression for p star q star, the projected one. That is nothing but the difference in the x coordinate. Is that okay? P star q star, just difference in the x coordinate. What is the x coordinate of q star? The original x coordinate plus the displacement of q star, which I have already seen as u x evaluated x plus delta x comma y. what is the x coordinate of p star, its original x coordinate plus the displacement of point P, which is ux evaluated at x comma y. So, this tells the x coordinate of the entire bracket tells x coordinate of q star, these two put together tells you x coordinate of p star. When you subtract, you will get the length of projected p star q star, that is a new length. The old length is delta x divided by delta x. Okay, let me repeat again. We want to find out the new length minus old length by old length. In new length, I will draw again, in fact, okay, I want the actual length of p star q star. I am just slowly exaggerating the angle just for understanding. Okay. I want this length, because alpha is very small. Instead of that, I take the projection and I let us say something like q star. Instead of that q star, I will take this q star and then find out only this length, assuming that this length is same as this length, which is valid when alpha is very small. Now, okay, let me now draw the projected p star q star, p star q star. What is this length of this line? Difference in x coordinate, that is all. X coordinate of q star minus x coordinate of p star. What is x coordinate of q star? Its original x coordinate plus the displacement. Remember, that is what we did in the earlier slides. To find out x coordinate of C, what did we do? 1 plus displacement of that point. Similarly, here its original x coordinate, what is that of q star? The original x coordinate is x plus delta x. To that you add the displacement of the point q. What is the displacement of point q? Ux, but evaluated x plus delta x comma y, that is this term. So, if you add these two, you will get the final x coordinate. Now, for point P, it has moved from P to P star. Now, we have to find out the x coordinate of P star. How do you do that? The original x coordinate plus the displacement of point P. What is the displacement? Ux evaluated at x comma y, that is what is this term. So, if you add these two, you will get the new x coordinate of P star. Okay. And of course, so when you subtract these two, you will get the length of approximated P star q star, the projection of P star q star. So, that will be the new length, the old length and the old length. Okay. So, let us simplify this. X cancels out, okay, and delta x also cancels out, and we are left only with the two displacements, and the denominator you have delta x. So, the numerator has the x displacement evaluated at x plus delta x and dx, anyway y is same. Okay. Now, we will take limit delta x tending to 0. What happens? This becomes a partial derivative of ux with respect to x. What is it we have done now? We have found a relationship between epsilon xx and dou ux by dou x. We have already seen that dou ux by dou x is nothing but a displacement gradient. Remember, when you took the one dimensional example, we had a wall, we attached a wire, stretched it, etc. The one dimensional displacement was dou ux by dou x. What is the alternate way of interpreting? This was one of the components of the displacement gradient tensor. Remember, we had displacement gradient tensor. The first term was the 1 comma 1 term was dou ux by dou x. When we wrote that, it looked like a displacement gradient, looks like a derivative. Now, we have given a very good physical significance for that term. When you look at dou ux by dou x, one mathematical way of looking at it is how x displacement varies with x, looking at mathematically. But now, look at the physical significance, because it has got a nice physical significance saying that normal strain. What does it mean? If at a point, remember all our point definitions, at a point take a small length, and based on this application of force, epsilon xx or dou x by dou x tells you what is the fractional change in length of that line segment at that particular point. Okay. Once again, as I told you, little difficult to imagine. At a point, imagine a small line segment, very small line segment. What is its final length minus original length divided by original length is represented by dou ux by dou x. which we call as normal strain. Okay. So, we get a physical significance for a simple derivative, partial derivative dou Ex by dou x. If this is clear, then we can go ahead with other things quickly. Okay. So, epsilon x x is equal to dou Ex by dou x. So, now whenever you look at dou Ex by dou x, immediately what should come to your mind is normal strain. Okay. Different representation itself, different viewpoint. Okay. Now, let us derive relationship between the shear strain and displacement gradient. Okay. Okay. Now, once again same assumption we make, alpha is infinitesimal, very small, alpha less than 1, tan alpha. How do you write tan alpha? Opposite side by adjacent side. Okay. So, let me draw that P star Q star, P star and then Q star. Okay. So, this length by this length, opposite side by adjacent side. How do you write difference in y coordinate by difference in x coordinate? Very well known to us, tan alpha, and this is our alpha, this is our alpha. So, difference in y coordinate by difference x coordinate, that is what I have written here, y q star minus y p star divided by x q star minus x p star, difference in y coordinate by difference x coordinate. Now, how to find new coordinate? Old y coordinate plus the vertical displacement. Okay. So, y q star is the original position of q, which is y, and then the vertical displacement of q. How do you represent? U y is a vertical displacement, but you are writing for q, which is at x plus delta x comma y. So, that is, so this put together will give you new y coordinate of q star, the y coordinate of q star. Okay. So, the original y coordinate, that is this is y. Okay. To that you are adding the vertical displacement, but evaluated at x plus delta x comma y, use the new y coordinate for q star. Now, let us do for p star, same like earlier case, the old y position plus the vertical displacement, but evaluated x comma y, because p is at x comma y. Okay. So, when you add these two, you will get the y coordinate of p star, and the numerator tells that difference in the two y coordinates, y coordinate of q star minus y coordinate of p star. Denominator is not new to us, we have already seen that in the previous slide, difference in the x coordinate of q star and p star. So, this denominator is not new to us, x q star minus x p star is nothing but the length of the projected, in our earlier case, projected p star q star, which I have already evaluated. Just for revision, x q star is a new position. So, the old x coordinate x plus delta x plus the x displacement, but evaluated at x plus delta x comma y, that gives the x coordinate of q star. X coordinate of p star is old x plus the x displacement, but evaluated x comma y. Okay. Okay, now, let us proceed further. Because we said alpha is infinitesimal, I am approximating tan alpha with alpha. This assumption is used in writing tan alpha as alpha. Right hand side, of course, the numerator y cancels out, in the denominator x cancels out, leaving us with these terms. Now, I will take limit delta x tending to 0. Look at the numerator, it is u y okay, at x plus delta x minus u y at x, and when you divide by delta x and take limit delta x tending to 0, you will get dou u y by dou x. Okay. You are dividing by delta x, the numerator and denominator. So, in the numerator you will have u y at x plus delta x, I am not writing the y, and then u y at x, okay, and divide by delta x, and limit delta x tending to 0 gives you dou u y by dou x. Look at the denominator, you are dividing this by delta x. Okay. So, this becomes 1 here, and you are dividing this by delta x and taking limit delta x tending to 0, you get dou u x by dou x. Okay. So, numerator becomes dou u y by dou x, denominator is 1 plus dou u x by dou x. Now, second assumption, infinitesimal normal strain. We have already seen that dou u x by dou x represents normal strain. I will assume that the normal strain is much smaller than 1. So, the denominator you can neglect dou u x by dou x, denominator becomes just unity. So, alpha becomes dou u y by dou x. What is it? Change of y displacement along x direction. Okay. Y displacement is vertical, okay, that is y, but now what we are dou u by dou x tells you how this vertical displacement changes in the x direction, okay. That is the meaning of dou u by dou x. Okay. So, the way in which the vertical displacement changes along the x direction, we have got a physical meaning for that, which tells you the rotation of the element p q. Now, repeat the same thing you will get for beta as dou u x by dou y. The displacement is along y direction, the displacement is along y direction, the derivative is along with respect to x direction. Here beta, the displacement along x direction, the variation is along the y direction, okay. They are the other way around, unlike the normal strain. Normal strain, see here you are seeing what is the change of x displacement in x direction, but alpha and beta you are looking at y displacement along x direction, x displacement along y direction. Now, gamma n t, we are now in the process of deriving expression for shear strain. So, let us write the definition for shear strain. Gamma n t is equal to pi by 2 and minus the angle r star p star q star, but the limit of q tending to p, r tending to p, okay. So, that you get a point definition of shear strain, okay. This is already seen. Apply that to the present case, it becomes pi by 2 minus, when q tends to p, r tends to p, what happens? Delta x tends to 0, delta y tends to 0 and this angle. So, this angle 90 degrees minus this angle r star p star q star, not for a finite value of delta x delta y, but in the limit of delta x delta y tending to 0. What is that angle? Alpha plus beta, okay. This difference is nothing but alpha plus beta. So, gamma x y, once again nomenclature has changed because our n t directions are along x and y axis, that is why replaced gamma n t with gamma x y, and the difference in angle is nothing but alpha plus beta. Substitute the expressions what we have got earlier, we have got an expression for shear strain, which is the change in angle. So, once again just like we discussed for normal strain, these gradients are familiar to us in the 2 dimensional case, though of course we did not sum up and discuss separately, we saw this gradient, but now you see when you sum up you have got a good physical significance. What is the physical significance? At a point imagine 2 small lines, and what is the change in angle from initial state to final state, that is what you obtain by summing these 2 derivatives. Look at them as derivatives, more mathematical, meaning change of u y with x, u x with y, but when you sum up you get the shear strain, a more physically meaningful quantity. Okay. Now, we made a few assumptions, let us summarize all of them, and this summary as a formal terminology called infinitesimal strain theory. So, we are discussing solid mechanics, strain in solid mechanics, we will discuss under this assumption. Remember some time back we discussed, we had a wire, a thread, and then we said it undergoes a small displacement or a small strain. Under that condition we said delta u x by delta capital X is approximately equal to delta u x by delta x, and then we said we are going to work with delta u x by delta x, and this is valid under the assumption of small displacement or small strain. This also is in line with that. All these are called infinitesimal strain theory. Now, it is an assumption in the case of solid mechanics. Why? When you subject a solid to a force, it can undergo a finite strain. This need not be always be, we said most of the time it is very very small, but it can be a large value also. We have assumed that they are very very small. That is why it is an assumption in solid mechanics. Later on you will see that when you go to fluid mechanics, we are going to carry over all that. It is not an assumption in the case of fluid mechanics. Okay? It is an assumption in the case of solid mechanics. And remember, we are discussing solid mechanics under that assumption, because we have come to solid mechanics to take some concepts to fluid mechanics. So, we are not discussing the general finite strain theory. We are only discussing a part of it, which is infinitesimal strain theory, so that I can take over these concepts to fluid mechanics, and that is not assumption there. You will understand that later on. Okay? So, that is the scope of this discussion. If you look at very rigorous solid mechanics book, they will discuss both finite strain theory and infinitesimal strain theory. We are not discussing finite strain theory, that will not give us linear expressions, that will result in non-linear expressions. That is beyond the scope of our discussion, not required also. Just learn whatever is required, whatever we can take over to fluid mechanics. Okay? That is okay. So, what are the assumptions of infinitesimal strain theory? What did we say first? Infinitesimal rotations, alpha less than 1, similarly beta less than 1 first. Then we said, when we derived expression for shear strain, what did we say? Infinitesimal normal strain, okay, which means that epsilon xx or dou x by dou x less than 1. And then because alpha less than 1, beta less than 1, obviously the sum is also very much less than 1, which means that the shear strain is also much smaller than 1. Okay. So, this complete set of assumptions is called infinitesimal strain theory. So, all our discussions are within these assumptions. It is not a limitation at all for us. We can straight away apply all this for fluid mechanics. Let that we will see much later. Okay.